Good morning everyone. Welcome to the first video on week 6 homework portal. Okay, let us start. This is for 10 marks, so I have allotted it for 10 minutes. Let me start with this video. So during electron capture, an atomic electron is captured by a proton in the nucleus. The stable nucleate thallium 205 will be formed when an unstable lead nucleate captures an electron. Write down an equation to represent this decay. Okay, so the nucleus is already given here, and there is an electron which has been captured over here. What is the boxes given over here? So what is this one here? This should be charge. So charge on electron is -1, and it does not have any mass number, so put it as 0 here. And then now you need to balance the reaction here. See, what will this be here? The neutrino will not have any charge, so it will be 0 here. Mass number is also 0 here. So something which you add with this should become 81. So this should be 82 here. Similarly, this should be 205 here. So now the reaction is perfectly balanced. Okay. Now let us move on to the next one. Very easy question. The unstable lead nuclei has a half-life of 15 into 10 power 6 years. Okay, half-life is given here. T half is given here. A sample nuclei consists of 2 micromoles. 2 micromoles means what? The mole content has been given here of the lead nuclei. Calculate the number of thallium nuclei being formed each second 30 into 10 power 6 years later. Okay, so he is asking you how many nuclei is formed every second over here. So if I first, when you read this question, you will not get to know what is it being asked. So what you do is you just write down the equation, then you will understand probably what is required. Number of thallium nuclei, number is given by n, formed each second, which means what? Divide by time. So which quantity corresponds to n by t? We know that dn by dt or delta n by dt will correspond to a quantity known as activity. So he is asking you the activity 30 into 10 power 6 years later on, and that too it should be mentioned with respect to in seconds. Okay, number of nuclei per second should be mentioned. That's what we need. Okay, now how do I calculate activity? What is activity formula? Activity formula is given by lambda times n. So if I know what is NT, what is NT? The number of thallium nuclei after this much time, right? And what is the value of lambda? Then I can take the product of this, get the answer. Simple. So therefore first we need to get the value of lambda. How do I get the value of lambda? Lambda is given by the formula ln2 divided by t half, right? Decay constant, which should now be 0.693 divided by what is t half? T half is 15 into 10 to the power of 6 seconds. 6 years we have. Okay, so therefore now let me write down this value, calculate this value. How much does it come out to be? Where is my calculator? Calculator is here. Okay, so I get the answer as 0.693 divided by 15 is equal to 0.0462. okay, let me write down that 0.0462, okay, into 10 to the power of -6. What is the unit here? Per year. This is what I get. Okay, next, first part of it is done. Now I need to get the value of NT. How do I get the value of NT here? Now what is N0? N0, we do not know what is the value of N0, right? It's only 2 micromoles given. Okay, now 2 micromoles means how many number of nucleus is it? That's what we need to find. So we know that so whenever we have 1 mole, okay, let us write 1 mole of a substance will have Avogadro number of molecules. 1 micromole of a substance will have 10 power -6 times Na. Then 2 micromoles initially will have 2 into 10 to the power of -6 Na. Na is nothing but Avogadro number. You can substitute it, you get the answer. Okay, now what we will do is, now what is happening over here? It's a radioactive molecule, and this is 30 into 10 power 6 years. How much is it? This is 2 half-lives, right? Let me do one more here. See, this problem is really bigger. Okay, after, now you had initially N0 atoms. After 1 half-life, this will become N0 by 2. After 1 more half-life, it becomes N0 by 4. Okay, so therefore after 2 half-lives, this is what is the value over here. What is N0? N0 is this value, because initially 2 micromoles of the substance were present, which is equal to this much number of atoms. So therefore after this much time, the number of molecules left, Nt, is equal to N0 by 4, which should now be equal to 2 into 10 to the power of -6 Na divided by 4. 2 ones are 2 twos are. Let me write the value of Na also. 10 power minus 6 into 6 into 10 to the power of 23. 6.02 you get across here. I'll just take it as 6 divided by 2. 2 ones are 2 threes are, which should now be equal to 3 into 10 to the power of 23 minus 6 should be 17. Now what is this? Number of nuclei after that time. Okay. Now what did I say initially? I said to calculate the value of activity, you need to get the value of lambda, you need to get the value of nt. We already got the value of nt. We have got the value of lambda also. Let us find out the value of A now. Simple. A is equal to lambda times nt, which should be 0.0462 multiplied by 10 power minus 6 into 3 into 10 power 17. Oh, I need some more space. Okay, we should ask IB to get more number of space. Okay, per year. Now, what is he asked here? Look at the question here. It is asked per second over here. Okay, which means convert the year into seconds. So this should be 365 multiplied by 24 hours multiplied by 3600 seconds. Now let us do all this and get the answer. Let me take my calculator. Without calculator, you cannot do this. Right. Now this 0.0462 multiplied by 3 is equal to so much, divided by 365 is equal to so much, divided by 24 is equal to so much, divided by 3600 is equal to so much. How much you are getting? 4.394, right? So I will write here 4.394 into 10 to the power of, what is that I am getting there? I am getting 10 to the power of minus 9 here, e minus 9, right? 10 to the power of minus 9 multiplied by 10 to the power of, see I left the powers here. 17 minus 6 should be equal to how much? 11. 11 over here. Yeah, we are doing it correctly. 17 minus 6 is 11, correct. Okay, so this should be 4.939. I'll write it down once again. 4.939 into 10 power 11 minus 2 is 2, which is nearly 439 nuclei. But you see, let us look at the significant figures here. See, here 2 significant, 2 significant, 2 significant, and so on. So therefore, this should be written as 440 nuclei per second. This is your answer. Wow, I got it correctly. 440 nuclei per second. Okay. Next, let us look at the next problem. The neutron number n and proton number z are not equal for the nuclei 20581 TL. Explain with reference to the forces acting within the nucleus the reason for this. The neutron number n and the proton number z. What is neutron number given by A minus z? And the proton number is z. Both are not equal. Okay, explain with reference to forces what is happening over here. Since they are not equal, the first thing is there is a short range nuclear force. Nuclear force acts inside the nucleus. Inside the nucleus. This is the first thing that happens over here. And then what do you need more? You need, because you see how many protons are there? 81 protons are there. Okay, so you need to have more number of neutrons to stabilize it. Otherwise, what will happen? It becomes radioactive, it will disintegrate, right? So this is what you need to write here. Okay, now let us look for the next one. Continue with this. Now, thallium 205 can also be formed from successive alpha and beta minus decays of an unstable nucleus. Okay, the decay follows the sequence alpha, beta, beta minus alpha. Okay, let me write down here alpha, beta minus alpha, which means what? Initially you get alpha, initially you have some nucleus X over here. After this you get alpha, then you get beta minus, then you get beta minus, okay, and so on. Then you get an alpha, and finally you get this value, which is this value 81 thallium 205. This is what you get. Okay. Plot of chart of the neutron number versus proton number is also given over here. What is the question? Draw 4 arrows to show sequence of charges to n and z as it occurs. Okay, here you need to show the sequence of charges. What we'll do is we'll write down the equation once again here. We'll write down the equation here. I have an x here, and alpha, how do I write alpha? Alpha I write is 2He4. Then this will be minus 1 E0, then you get minus 1 E0, then again I get 2He4, 2He4, then finally you get 81 thallium 205. This is what I get. Now let us understand what are the type of nucleus do I get over here. So here, what is the final nucleus? That we need to look at the path over here. See, if this has to be 205, this should be larger than 205. So what should this be? See here, first it will lose 4 nucleons, then it becomes some nucleus, then it will lose an electron, then again an electron, then again a nucleus, and so on. So total number of nucleons lost over here should be 205 plus 4 plus 4, which will be 205 plus 8. This should be 213 over here. Okay. The same accounting, if I do it over here, the total number of protons it loses during this process is 2 plus 2, 4, 4 minus 1, 3 minus 1, 2. So it loses 2 protons during this process, okay, to yield this particular nucleus, which means I should add 2 here, which will give me 83 over here. So thus the parent nucleus earlier was 83x213, and after emitting these radiations, it got something like 81 208, 81 thallium 205. And it is said that 81 205, 81 thallium 205 is this part, this black color one which is given here. Now we need to identify this one. Where is this one here? 83x213. Now in the graph, now how many neutrons will be there? This is the total number of nucleons. Okay, 213 minus 83 will be equal to how much? 3 minus 0, 11 minus 8 is 3, and this is 130. Okay, so your neutron number should be 130 and your proton number should be 83. Where does this come here? This is your 83 here, and the neutron number is 130. It should be over here. Okay, from here, what is the sequence of nucleus that comes down? That's the question. Now, when it emits an alpha particle, what will happen? 4 nucleons gets reduced, and 2 protons are increasing. Sorry, 4 nucleons are getting reduced and 2 protons are also decreasing. Which means what? The next nucleus that will be formed would be 2 protons reduction. 2 protons reduction. 83 becomes 81 here. Okay, here the new nucleus it's formed will be 81 over here. Will be 83 will become 81 over here. 81 here. And what will be this one here? 213 minus 4. 213 minus 4 will be 209. 209. Where is 209? So 209 here. Total number of nucleus here. 209 will be the total number of nucleus minus 81. If I do this, 9 minus 1 is 8. This will be 128. So you should plot a coordinate at 128. This should be 81 and 128 should be somewhere over here. So now what I do is I can indicate this by a line here. So this is what. Now this shows you a alpha decay. Now what happens in a beta decay? In a beta decay, if you see, this is not at all changing. When this is not at all changing, then it has already come to 128 here. The next point should also be 128. Next point should also be 128. That means you should not get any points below 128 or above 128. It should be along this line. This line. It can either go like this or it can go like this over here. Okay, let us understand that also. Now what's happening here? See, when 2 units are reduced, the resultant nucleus, the proton number also reduces. When you say minus 1 over here, okay, it's opposite side, right? Which means the proton number should increase for the new nucleus, which means you will get 1 point here, okay, because 1 unit over here. So 1 point here, which you will indicate it by like this, and you will get 1 more point over here, 1 more point here, which is indicated like this. Let us verify it if you still want to know. Okay, so this is what is this now? This is your 83x. This is your 83 213. For time being, what I will do is I will not write 213, I will write 130 also along with it. Okay, proton number, see, this is your proton number, this is your neutron number, this is your total nucleons. I am written this one here. It's taking some time, but anyway. So after alpha decay, now what's happening? You get 128 here. What is 128 here? Neutron number. So let me write this as some x1 here. Okay, I do not know what's the nucleon here. What is the nucleus here? I'll write x1 over here. Or maybe since x is there, right? I'll do one thing. I'll write this as y here. I'll write this as y here. This is y. And what is the proton number here? Proton number is 80 here. 80 here. And this should be 128 should be here, right? 128 should be here. And what is this this one? Total number of nucleons 128 plus 80, which will be 208. Okay, see, 208. I have got this one here also. Okay, 213. Just a minute. 213 minus 4, right? It should be 209 here. 209 here. Okay, then this should sum up to be 209, right? Where are we making a mistake? So 130, this is 83 minus 1, this is 81 here, I'm sorry. This should be 81. Hey, I made a mistake here. See, this is 81. This is 81 here. 81, 128, 209. Then, now let me call this nucleus as A here. Now, what will be this nucleus A here? See, this is now, see, 82 here. 82 here. And what is this here? This is 128 here. And 82 plus 128 shouldn't be, sorry, this is your 128 here. And this will be your total number of nucleons. Now, what is this one? Let me call this as B here. This will be 83 here. And this will be what? This will be 128 once again. 128 once again. Now, you see, whenever there is an alpha decay, there is a diagonal like this. Whenever there is a beta decay, it's a straight line like this. Now, this is the third nuclei form. This was your first nuclei. This was your second nuclei. This is a parent nuclei. Then second nuclei, then third nuclei, fourth nuclei, and finally you get the final nuclei. Where is the final nuclei? It's here. Now join this also here. Join this also here. Okay. The diagram appears to be very clumsy. Let me rub out, erase out all this. Maybe you can pause the video and see what's happening over here. So it becomes clear for you. The final value, final diagram should look like this. I will remove the whole thing and I will rewrite this once again so that you get to know how should the plot look like. If you still have any doubts, this is bit confusing, bit problematic. People don't understand it so easily. Okay, but anyway, nothing is difficult. Okay, so what you do is, if you still have a doubt, you can write back to me. I will explain it in the next video. Make a detailed video on how do you arrive at the decay series. Okay, it's a very important problem. Okay, so this was your parent nucleus and this was your new nucleus, which came because of your alpha decay. Then came your beta minus decay until here, right? Until next once again. So you should indicate this by an arrow. Okay, then once again an arrow. So this is your next beta minus decay, and then you once again you get this one here. So this is your alpha decay. See here, two boxes are being crossed, two boxes are being crossed, right? This indicates your alpha decay, and this beta minus decay only a horizontal line. Hope you understand this. Okay, if not, do write back to me. Okay, so we have got the decay series. Next, that's it. Okay, fine, we have come to an end to this. Thank you. See you again in the tomorrow's video.